We have 1.9 dB loss budget, and we have for 13, sorry, on 4 we have 1.53 dB loss budget and maximum 150 meters. Then for the 100 dB also it's the same thing. 100 dB and 40 dB they have the same loss limit. That's interesting. So that's where the confusion starts to get into your head. Then it's going to get a little bit more complicated because then you go back and you say, oh, for what 500, didn't I have 2.55 dB loss, maximum allowable loss? Okay, reasonable. Then you go back to the standard charts and you say, oh, oil 500, and then you come down here. Remember we had 10 gigabits SR, right? And then you look, and then you zoom in, and you say, oh my God, where is the standards? There is no loss limits even for multi-mode running at 10 gig. Didn't we have it before? So this is a lot of confusions. You have to use the right method in order to get to the bottom of the story and to whether to see you have a pass or a fail. We have a standard for the single mode, but there is no standard in here. But in the channel, there was a standard. So which one should I use? This one or that one? It's very, very critical to use the right one. And then if you want to use a channel, then you will be in a nightmare. Because remember, we had 2.6 dB loss, right? At the beginning of OF 500, right? Okay, if I want to go with the channel standard, I will be having 0.75 dB allowable loss here, 0.75 dB in this middle section, and then in the corner 0.75 dB. I'm already at 4.4 times 0.75 is 6 dB, right? 0.7, no, sorry, 3 dB. 0.75 times 2 is 1.5 times 2 is 3, right? So then now, all of a sudden, if I use channel then for my data center, then I'm totally wrong. I have to use the application standard. So you need to be educated on which standard you need to test against for which environment. Don't use a channel standard in a data center where you have MPOs. You're going to get unrealistic results. Okay? So, going back again, if you remember, we talked about these two tests. In a data center, they are mandatory. You have to run a tier 1 test and a tier 2 test based on 14763-3 standard. You have to do both. It is not an option. In the channel side, if you're running a building test, it's recommended, but here it's mandatory. You have to do it. The complementary test is mandatory, especially when you go to the basically TIA 568C3. Okay, we discussed this already. I'm not going to discuss these again. One of the things that I would like to say here is that per standard, we are allowed to basically have the meter side removed. So we are allowed to touch the meter side, but we are not allowed to touch the light source side. So that's why they recommend this one, and also they recommend to have ICA, or what we call interchangeable adapters. And we do have it, so you don't need to have a hybrid port. You can change the adapters, whether you have SC or ST or whatever you have. You can, basically it will come out of here. I will show you. You can change the adapters per your requirement. So you can run what we call method B. You don't have to do modified method B in your testing. So again, this is allowed, and this has the least amount of variability. Okay, now you can see now when you use a regular port, your one jumper, remember that 0.3 or 0.6 dB that we had, it will pile up and you will not get realistic results, or uncertainty will go up. Whereas if you use a TRC port or test reference port, because of the low variability that they have and high performance that they have, the contribution in the losses will be naturally less. And then of course one port will have less variability than 3 port and then 2 port. So that's why we say this is the best way to go, especially when you go to the data centers, where you have very tight margins, you have very small budgets, and then your bandwidth is huge. Okay? Okay. Now, the other challenge that has come in the 140 gig standard and even to some extent 10 gig is what we call encircled flux. Okay? And again, this idea was brought about to improve the certainty or reduce the uncertainty of your test results. Okay? And that's because, again, your budgets are becoming less and less, so you have to have more accurate results to see whether you have a pass or a fail. If you have more budgets, more headroom, who cares, like this room. But imagine this ceiling coming down on my head. Slowly, I have less and less space to breathe. So fiber is like that. It has less and less space to breathe, and you have high bandwidth, so you need to have things for testers that they do the right measurement and give you realistic results. Okay? This portion of the presentation is a little complicated, so please bear with me. Okay, now, as we said, we have two types of light sources when it comes to the tester side. So a typical tester will either have a VCSEL light source or an LED. Alright? One we call underfield, which means it's not filling the entire pipe of the core. The other one is called overfill, which is filling the whole core. Alright? Now, the problem started with this story. You have light source A, right? And you have your meter. You test and you get let's say 1.86 dB loss, as you can clearly see here, right? Then you bring the second tester in, light source, and you get a different result. So which one is right? Is the other one right or this one right? That has been the issue, that the involvement of the technology that goes behind the light source of this guy is quite complicated. Not only from us, but from everybody else. Any light source that is proper, they have gone through a lot of evolution, which I'm going to discuss with you now. Okay. The first type of light source in the days of the 100 megs that we had, 100 gig, 100 meg, we were talking about late 90s or early 2000s and so forth. They had what they called CPR, or coupled power ratio. So what they did basically is very straightforward. They took because every one of these that comes out of the factory, especially for Fluke, every single one gets individually tested. So it's not a random test, every single one gets tested and then they are shipped to you. Alright? So what they did was, they did what they call coupled power ratio. So they sent a light into two different kind of fiber. One was the same light, so doesn't matter what kind of light, but the same light was sent into a single mode, and they also were sent into a multi-mode. And they took the difference between the two, and they called it coupled power ratio, and they grouped it. So they said group 1, which is overfilled, then group 2, group 3, group 4, group 5, group 6, group 7, and I think that's the last one. Okay, so the higher your CPR, coupled power ratio, the more toward the overfill you were. Alright, that was the grouping that they had. And they would certify that you had a CPR1 from Fluke on your tester, on your fiber tester, to be able to do a proper testing. This is the first thing that they did. Okay? This is pre-2006. Now, with the introduction of gigabit Ethernet and running fiber on gig, then they saw that the results were not repeatable. So that means you're not getting the same results. There was just way too many issues with the results. Okay? So they had to devise a new way to test these light sources on the testers to make sure they are within a certain range. Okay? And that one is called MPD, which is mode power distribution. Okay? And they had to really do a lot of head scratching to do this. As everybody knows, the light source of, the light that goes into the cable itself is invisible. Everybody knows that. It's beyond the visible spectrum of light, correct? Everybody, we were discussing that you should never look inside the fiber with a scope because the light will damage your eye, right? They devised the little box for testing purposes that would convert the light into a visible format. You could see it. All right? You could see it. Then they ran some advanced mathematics for different modes. These are all multi-mode now. We are not talking about single mode. I'm purely talking multi-mode right now. Okay? So what they did was they went ahead and they ran some advanced mathematics to measure every single mode's performance, and they created templates. Okay? And this is the template. And they said different modes have to run between this template. So imagine every single, and these tests are quite cumbersome. Every test takes at least between 36 minutes to 45 minutes. So every single light source that came out of Fluke factory was tested to make sure that they fall within this template to give you realistic results. But the problem was that you could not figure out what exactly was there. You had here the mode power, and then you had the mode number, and it was really complicated, and they had to do a lot of normalization and so forth. And this gap was way too much. So what they did was, they came out, and this is, for example, the Bexel. So Bexel for sure doesn't fall into this range. But LED will fall into this range. Okay? Now, so what they did was they used the same technology, but they redid the math work, and they made it more comprehensible, and they created what is called encircled flux. Okay? Now, within the encircled flux, the mathematics was done in a way so it is more understandable. You had still your mode power on the vertical axis, however, here was the core diameter. So you could see the behavior of the light that went through based on power. You could see from the center of the core how much power was distributed all the way to the edge of the core. This is the story of encircled flux. Now, once you look at this, then they created a secondary template. So they said, now if you look at this band, this is where a light should sit. A light source for a tester should sit within this band. Anything beyond this will be overfilled, anything above it will be underfilled. So those category 1, 2, 3, 4, 5, 6, 7, this is category 1, this is going toward category 7. And this is again the diameter of the fiber, and this is the normalized power on the encircled flux. Now, what happened was they defined the boundary, and then they said that the light source that should be EF compliant has to fall within this bandwidth. This is not a standard, it has nothing to do with Fluke. This is irrelevant to Fluke. This is coming out of the standards because they had to get repeatable test results and reduce the uncertainty on the measurement. Okay? For 100 gig, 40 gig, eventually 140 gig, right? So you can see a light source that is produced, which is EF compliant, from one tester to the other tester to the other tester to the other tester, has a maximum variability of 10%. Okay? Now, if you had the LPD light source, your variability is 40%. So that means one tester will give you a great pass, and the other one will give you a horrible fail. 40% variability. That means if you had a tester that was LPD compliant, you would buy, this gentleman would buy a tester, will get a pass, he will get a fail. And in data center, in 100 gig, 40 gig, that just can't happen. And that's why it is part of the 14763-3 standard that for the higher bandwidth requirements, 40, 100, even 10, you have to have an EF compliant light source on your tester. Even some companies now, even for your 25-year performance warranty, I cannot name the company now, but one of the best known here in this region is making it mandatory. You have to have a DTX EFM2 module for multi-mode. It has to be encircled flux compliant module. Otherwise, you will not get your 25-year performance warranty. Sorry to say. So you have to have this. All right?
EF compliance is not there in the GTX 1800?
Yes, it is. We have a EFM2 now. I will get to your question later. There's some common questions, I'll get to it. Okay? So, all right, now, what we did was, let me go back, sorry I jumped. Okay, now, a while back, when this 10 gig story was coming out, we came out with what we call basically mode conditioner. So that means, doesn't matter what kind of light source you had, it would condition it and it would make it EF compliant. Okay? So we have had this for a long while, 3-4 years we have had this now. Okay? So it would retrofit legacy testers, like if you go to the DSP series, it will support it, microscanner will support it. Okay, and it would make the light source compliant. But let's take a look at the drawbacks. Expensive, number one. Very expensive. It is clumsy. You have to drag all these boxes here and there, right? Then you had to purchase individual mode conditioners for different kind of connectors that you had. Because you cannot replace the connector here. It is done in factory and it goes through that box that I showed you that creates the image and puts it onto the template and it makes it EF compliant. So you have to imagine, you have ST, LC, all ST, you have to spend more than the tester itself on the mode conditioner. Expensive, right? Okay? And then if it wear out, which naturally will wear out after, let's say, maybe 5,000 or 3,000 tests, you have to buy a new mode conditioner. You couldn't change the connector. That's the problem with mode conditioners. Okay? So, typical questions regarding this. Okay. MFM2, multi-mode, which a lot of people are using, is it MPD compliant or not? The 40% variability that we discussed. Well, I have news for you. Even though it is not EF compliant, but still Fluke put it into the in-circuit flux template and made sure that the combination of the MFM2 and the Mandrel will give you what you want. Right? So we fell within that template. Very small variability. It's not in-circuit flux compliant, it is within the same template. Whereas the EFM2 is in-circuit flux compliant. Okay? It has to be, if you want it, some companies they say we want in-circuit flux compliant modules to be used.
Just to add on top of that, that instead of the 40% variation, you get a lot better variation.
Yeah, of course.
So that's the whole idea behind having that signal within the in-circuit flux model.
It's below 10. Now. Alright? See? It's from 10 gig and up. 10 gig, 40 gig, 100 gig. But some companies are running now. If you're running OM3, OM4, if you want to get 25 performance, they will want it from you. Doesn't matter what you run. You might not run anything on it. Yeah. Okay? So you can see all the explanation here, which we discussed. Okay. The next question is, can I replace the plug? No. As we mentioned before, you can't. So you have to buy the EF compliant mode conditioners. It has to be done in factory because you need that box to create the image and do the mathematics and the template and all that stuff. Okay? Now, the other thing which is very important that a lot of people ask, they say, okay, all right, I'm going to get an EF compliant device. All of our devices are EF compliant. I'm going to throw a patch cord in there and I will be having an EF compliant, thing. And the issue is no. If the light that comes out of here is EF compliant, doesn't mean that the light that comes out of the tip of that LC here is also EF compliant. You have to have a specific cord designed for EF compliance. Okay? And also the measurements that they have done, even though this is your template, If you use a regular cord, even though the light that comes out of the tester is EF compliant, it will fall below the template. Right? So you have to have a specific cord for this. So it will not work. Even though your device is EF compliant, that cord is very critical. Okay? This is regarding the EF versus non-EF, which we already discussed. I'm not going to go through it again. And the difference between the results. So if you have a EF, if you pass this one, you pass this one. If you get a fail here, you will get a pass here. But if you fail here, also you might get a fail here as well. So EF compliant will give you realistic results. That's what we want to push and inform you about. So we don't want to have, issues with the customer coming back and saying the link doesn't work. Okay? Now, so a wish list would be typically to have an EF transparent test reference cord, affordable price, test reference cord performance, so the cord is EF compliant, the cord is affordable, okay? And it has the same performance that is required for TRC, and it shouldn't be clumsy, and it should be interchangeable. Well, we have it. This is the EFM2, and these are the cords. These are actually the encircled flux cords that you see with the circles. These guys here. This one and this one. And you might ask why it's not on the other side, because it goes always on the light source side, not on the mirror side. Okay? Next topic, I'm going to briefly go about MPO. MPO stands for multi-fiber push-on connector, which allows you to go from, for higher bandwidth, for don't touching your data centers if you want to migrate from 10 gig to 40 gig to 100 gig. It makes life a lot easier because everything is pre-terminated. However, it has its own challenges. For example, if you go with cassette, because of the fiber technology, you know that you have to use every receive goes to the transmit, every transmit goes to the receive, so it's a cross. So you have to have cassettes that are flipped. One, so it's the polarity is proper. You need to check, you need to take care of the polarity. So you have to check about control those situations. Sorry, this jumped. Oh. Okay. Now, one of the nice things about MPO is that it has enough capacity that you can migrate without touching the infrastructure to higher bandwidth requirements. That's one of the nicest features about MPO. Alright? Very low link cost budgets. Everything is, especially on 1Q and 4 standardized. They are very high performance. By the way, one question before I continue. Does anybody know what, we talked about 1Q and 4, they call it graded index fiber. Does anybody know how it works? Why they created this thing? Okay. If you remember, we talked about multi-mode. Multi-mode has different modes, right? One goes up and down, one goes in an angle, one goes straight, right? Well, it's typical that the one that follows the shortest distance gets across first, correct or not? So the lower order mode, which is in the middle, will get there faster than higher order mode, right? So in order to take care of that, what they did was they increased the index of refraction of the core of the fiber, so the middle mode or the lower order mode will go slower, and then the next grade would be a little bit index of refraction higher and higher and higher and higher and higher. So what happens is when you transmit the signal in a multi-graded index fiber optic cable, all the signal gets across at the same time. That was the whole purpose of OM3 and OM4, which is expensive to manufacture, and that's why it is, because of this grading issue that they have, so they can transmit the signal at the same time.
Laser optimized.
Sorry?
That's why it's called laser optimized.
Yeah, it's laser optimized, but a lot of people don't understand what laser optimized means. I'm explaining what is happening inside the fiber in order for people to understand what's going on. Exactly. Yes. 3 has a lower number of indexes, and 4 has a lot more. 1 and 2 doesn't have index or refraction. It's just straight. Okay. So anyhow, and then you can leverage the cassette system, pre-terminated, where it becomes everything easy to install. However, from the testing side, it becomes a nightmare. Imagine that you, in order to do MPO testing, you have to do set referencing that we discussed. Then you have to put a fan-out cable which has connectors on one side and MPO on the other side. Then you put your MPO link in between. Then test one. Then move this again up, and then do the testing and up and up and up. So you can do all 12 cores, right? It will cause confusion. You have to do a lot of head scratching, polarity, test limits, documentation, right? So Fluke has made all these issues of complexities, incomplete things and tedious things that we have to do for the MPO, they have made it unified. Because sometimes you go into the environments that the cassettes are straight, the cable is flipped, sometimes you go to the places where the cable is straight, the cassette is flipped, sometimes you go to places where the cassette is straight, the cable is straight, the other cassette is straight, one patch cord is flipped, the other patch cord is straight. So the combinations become too much, and usually when you go for the remember, when you do testing, you're not necessarily the installer, so you don't know what they did. Just go there for testing, right? As an engineer. So what they have done is we have devised a solution that will automate this process for you. It will check for polarity. It will check one by one, every single one automatically, and you can document these results. Okay? And it will go, of course, to linkware. It is very fast, so you can test all 12 fibers at once without worrying about the polarity and doing what. Okay? 6 minutes in comparison to when you want to do individual ones, because every time you have to set reference, all that stuff. Here we set reference once, we connect the MPO link, and we go home. So, and then it will consolidate all the results in a single document. So you can see 20 seconds. It's very, very fast. Okay? So it will measure loss, power, polarity, limit testings, verifies both MPO permanent links and channel links, test trunk cables, patch cords, and cassettes. So you can check for a multitude of solutions that you have for the MPO. And again, remember, it is coming. This MPO is coming. Whether you like it or not, it is coming. It's knocking on your door. So better to know about it and know about challenges and be prepared how to overcome these challenges.
Can the machine certify the complete channel with method A, B, or C? Or
no, we cannot certify with this. With this device, no. But I think it's on the roadmap.
It's power. It's measuring the power. Because at the moment, there's no requirement for certification of MPO. So at least you need to make sure that the link is okay. So when you're doing your troubleshooting, first, is it the problem of the MPO cable? Is it the problem of the cable or the problem of the cassette? And many of the time it might end up that it's the problem of the cable because the installation went wrong and they damaged the cable. So this tester can verify the cable if it's working well or not. Then if the cable is good, then you start doing problem isolation that might be this cassette or that cassette might have a problem and you continue. Yeah. So first problem isolation is how fast can you detect if the cable is good or bad. And this is how within 20 seconds you could do it, rather than 6-7 minutes that you have to do it individually, core by core analysis. And this is the value. What you need now is figuring out if this is okay or not okay. With development of technology, maybe at a point of time, requiring certification might be a need, but today's, according to, again, standards, there's no certification. We do only power management. If you need certification, then you need to go with a 6-minute wait. Fan out individual core by core. That's another thing.
Then you have to worry about all polarities.
Yes. But since everything is recorded here on the machine, you can look at the data and verify core by core what is the reading that we can get.
We talked about the basically extended certification that is required for data centers, so please make sure that you are doing that. So this is a tier 1 test, and on top of that, you can do tier 2 test. As you know, all of our equipment now, they can take care of both of them on the same platform, whether you have a DTX or Versic DSX, you can do both of them at the same time. There's no issues on that. For complex channels, okay, you need to, again, understand the segments and the links and the environment you're testing for, okay? So you can see here, for example, specific connectors are misperforming, whereas the limit is 0.75. This is only visible by OTDR. There's a channel will not show you. You might have a total channel pass, if you remember I told you about. Remember, we discussed if you do an optical loss test set, this one, top one, to 2.4 total loss, whereas when you do an OTDR test, you can individually see individual components, performance and behavior, and get a pass-fail result. So that's quite common. And then the nice thing about the OTDR that we provide is that it will give you the full channel. It will tell you whether you have a ghost or you have a splice or you have a coupling, how much loss it is against the standard, whether you have a pass or a fail. And so you can get individual-based pass-fail results, as I mentioned, which is not seen in any other OTDR as I know of. So we get pass-fail, and you can even certify the interface as well, and give you pass-fail for that one. So you can see with the OTDR graphic user interface, you can see where the problem areas are, and rectify the problems, and then you increase your budgets for future migration to higher bandwidth requirements. Okay? So you can zoom in to the different locations. You can see physically at what location those problematic areas are, and basically resolve the issue. Another thing that you can see even with OTDR, especially this OTDR, because of its capabilities, even if you have a tight tie wrap, it's visible. You can see it as a step. So all of these things can be seen with the OTDR. Gainers also, as I said. So there's different things that you can understand, the ghosts and so forth. I'm not going to go through this. It gets quite complicated and cumbersome, but you can do a lot of measurements. So you have a gainer here, you can see that the input signal, it goes higher, so that means energy is gained. So there's issues that you need to resolve, something like this. And those are mostly based on the environment that you have that you can rectify. So you can work your way, you can figure out the polarity, then you can look at the, basically walk in the fiber and see where the light is coming out, okay? Pinch the fiber, and, okay, for the break and see the light will shine out. So you can see all of these things, and OTDR is the best solution at the end of the day for basically trying to troubleshoot. All right. We have another product which is called Fiber Quick Map, and that one is basically will show you where the problem areas are. So it will locate the problem. It's not a OTDR, but it will locate where the problem areas are. So when you run basically test on this, you can see the losses and you can see